Let's look at several ways that we can interpret the derivative at a point. One way is the slope of a tangent, and this is the way that we've looked at already a few times. Imagine we have a function y equals f of x, and I were to pick a point P and label the coordinates of P as being a and f of a. Then I have a point P. I have a slope, that's f prime of a. Remember, the derivative we're interpreting as the slope of the tangent line. So if I have a tangent line, this line, say in blue right here, f prime of a would represent the slope of that line. And then the tangent line is f prime of a is equal to y minus f of a over x minus a. And that's just the slope formula, change in y over change in x. I can rearrange that and write it as y minus f of a equals f prime of a times x minus a. And so this is a way of interpreting the slope of a tangent line using the derivative. So let's look at an example. Let's find the equation of the tangent line to y equals 2 square root of x plus 1 at the point 3, 4. So in order to do this, I need to calculate a derivative. And here's my point, and imagine that this 3 right here is my value of a. So I want to find, in this case, f prime at 3. And I know I have y equals this function. You can imagine the y as being our f of x here, so I'm looking at f prime at 3. And I can use either of the two ways of finding this, the h approaches 0 or the x approaches a. I'm going to try the x approaches a method for this one. So I'm going to let x approach 3. And then the formula was, if you recall, f of x minus f of 3 over x minus 3. Okay, so now I can just plug into this. So I have the limit as x approaches 3 of f of x, that's 2 times the square root of x plus 1, minus, and now I have f of 3, that's 2 times the square root of 3 plus 1. And then all that is going to be divided by x minus 3. And let's see, I can simplify this a little bit here by noting that I have a very nice square root here. 3 plus 1 is 4, and the square root of 4 is 2, and so this will be 2 times 2, which is 4. So let's rewrite that. So I have 2 times the square root of x plus 1 minus 4, all over x minus 3. Now the normal thing that you would do in a situation like this where you have a square root is to multiply the top and bottom by the conjugate of this. So I would multiply the top by 2 times the square root of x plus 1 plus 4. And if I multiply the top by that, I also have to multiply the bottom by the same thing. And if this works, then we should get something that simplifies quite a bit. So again, I have this equaling the limit as x approaches 3. And let's see what happens. So we have to FOIL out the top here, first, outer, inner, and last. So the first term would be 2 times 2 is 4, and then the square root will go away here. So I'm going to get 4 times x plus 1. And then the cross terms should cancel. I have a 2 times the square root of x plus 1 and a 4, and then I have a 2 times the square root of x plus 1 and a negative 4, so those are going to go away. And then I have a negative 4 times a positive 4, that's going to give me minus 16. And then on the bottom, I could multiply this out, but I'm not going to do that because I know that something's going to cancel here, that x minus 3 is probably going to cancel, so I'm just going to leave it like the normal way here without multiplying it out. Okay. And so what happened here? So I have a 4 that I can factor out of the top here. Let's do that. So I still have my limit, haven't taken the limit yet. And I have a 4, and then what would be left over? I would have an x plus 1 left over minus 4 up top. And then on the bottom, same thing, x minus 3 times 2 times the square root of x plus 1 plus 4. And now let's see, x plus 1 minus 4 is the same thing as x minus 3, and that's going to cancel with the x minus 3 on the bottom, and I kind of knew that was going to happen, so that's going to go away. So this leaves me with the limit as x approaches 3 of 2 times the square root of x plus 1 plus 4 on the bottom, and then on top, I just have 4. And I think I'm ready to actually take the limit now because I can put a 3 in here. 3 plus 1 is 4, and the square root of 4 is 2, so I have 2 times 2 plus 4 on the bottom, and then a 4 on the top. So this is the same thing as 2 times 2 is 4, 4 plus 4 is 8, 4/8, which is a half. Okay, so now that I know the slope of the tangent line, I can write this as 1/2 equaling, and I can do change in y over change in x. So remember that my point 3, 4 is what I'm going to use here. And so I have on the top y minus 4, and on the bottom x minus 3. And I guess I'll simplify this. So I can rewrite this as y minus 4 equals 1/2 times x minus 3. And if I really want to, I can solve for y. I can bring the 4 over to the other side. So I would get y equals 1/2 x, and then I would have minus 3/2 plus 4. And minus 3/2 plus 4 is 5/2. So I would get 1/2 x plus 5/2. So that's one way to interpret the derivative at a point. Another way is to look at it as a rate of change. And this is something that we've also seen before. So I'm going to look at a specific example. And in this case, I'm going to look at a person throwing a rock off of a cliff. So here's a cliff, here's my person, and they're going to take the rock and they're going to throw it straight up in the air so that it comes straight down and lands somewhere down here. So all of this is happening just in a straight line right here. And I'm going to let S represent my displacement. So this is the displacement of the rock. So I'm going to let positive S be in the up direction here. And so what would S prime of A represent? Well, that would be the rate of change of displacement with respect to time at t equals A. And we have another name for that. We just call it the velocity. So that's the velocity at t equals A. The initial height, let's say that's 45 meters, and the initial velocity, we'll say that's 20 meters per second up. And so my formula that I would get for the displacement would be S of t, S as a function of time, would equal 45 plus 20t minus 4.9t squared. And if you're not sure where that came from, it's actually something from physics. So you don't need to know too much about where that came from for the calculus to understand that. But if you do happen to know physics, then this probably will make sense. This is something you see in one-dimensional motion. So here's a graph of the displacement versus the time. And so this is the displacement on the y-axis, and this is the time on the x-axis. Time is in seconds, and displacement is in meters. And the question that I want to ask is, what is the velocity of the rock at t equals 2 seconds? So velocity, we know, is the rate of change of displacement with respect to time, which is the derivative. And the derivative we saw before, you can think of that as the slope of the tangent line. So here's 2 seconds. And if I look at what the tangent line might look like here, it looks pretty much like it would be a flat line. So we should expect when we calculate S prime at 2, which is what we will do to find the velocity of the rock at 2 seconds, we should expect to get something pretty close to 0. So let's try and calculate it. Okay, so here is the formula for the displacement as a function of time, and the question that we wanted to ask is, what is the velocity of the rock at t equals 2 seconds? So in order to do this, I actually want to calculate S prime at 2. That's the derivative at 2, and that's something that will give us the velocity. And remember, there's two ways to do it. We can use the formula as h approaches 0 or as x approaches 2 in this case. And I'll do the h approaches 0 one since I used the other formula for the other part of the problem. So let's look at S prime of 2, and I'll write that as the limit as h approaches 0 of S of, and I have 2 plus h, minus S of 2 all over h. So A here that we would normally use in the formula is going to be 2. And so let's plug in here. So this is the limit as h approaches 0 of S of 2 plus h. So I'm going to take my formula for S up above, and everywhere that I see t, I'm going to replace it with 2 plus h. So I get something that looks like this. Okay, and then I have minus S of 2. So I'm going to do the same thing, but just replace all of the t's with a 2. All right, and all of this whole thing here is all over h. So let's try and simplify this a little bit here. So I have limit as h approaches 0 of. So I have 45 plus, and then I have, let's see, 20 times 2 is going to be 40, and then I'm going to have a 20h. And then I'm going to have minus 4.9 times, and then this thing, 2 plus h squared. Let's write that out. So that's going to be 4 plus 4h plus h squared. Okay, minus, and then I have a 45. And I have a minus 20 times 2, that's going to be 40. And then it'll be plus 4.9 times, well, 2 squared is 4. So it's going to be 4.9 times 4. All of this is still over h. Okay, so this is the limit as h approaches 0 of this thing. And let's see, a bunch of stuff cancels. I have a 45 and another 45. I have a 40 and I have a 40. And I have a negative 4.9 times 4 and a positive 4.9 times 4. So that is going to go away. So what's left? I have a 20h. I have a minus 4 times 4.9 times h. So that's going to be 4 times 4.9 times h. And a minus 4.9 h squared. And all of this is over h, and now I think I can get rid of the h because I have an h in every term, so I can cancel it out. So this is the limit as h approaches 0 of 20 minus 4 times 4.9 minus 4.9 times h. And I can take the limit. Let h go to 0. This last term goes away, and I get 20 minus 4 times 4.9. And if you calculate this, you get something pretty small, 0.4. And that's about what we expected. We thought we would get something that's pretty close to 0 here. We end up getting 0.4. So we saw that the velocity of the rock, which is what we were trying to calculate, the velocity is 0.4, and the units on this would be meters per second. So this is our distance over our time here. So we got something that's pretty close to 0. So a natural question to ask would be, how would you find the time at which the velocity is exactly 0? So this is something I'll let you think about. We'll come back to this question in a later series of videos. We'll actually look at this in great detail. But for now, see if you could figure out how would you find the time at which the velocity is exactly 0.